Okay, so the next problem I'd like to do is number 3. We're dealing with something called a Norman window. It's a specific style of window. I'm sure we've all seen this before. It takes the shape of a rectangular window with a semicircle on top. Okay, and the information that we know about this particular Norman window is that it has a perimeter of 200 inches. So that's the length all the way around this thing. We're asked to find a function, a of x, that represents the area of this window, where x is the length of the base, okay? And again, my image here kind of split the text apart a little bit. I'm going to fix that before I send this out to you guys. So let's start breaking this problem down. Let's think about what we know first of all. We're told the perimeter of this thing. But how do you find the perimeter of a shape like this? So E3, that's what we're working on. We have this Norman window. I'm going to do a little ... there. Okay. And all we know about it, as far as its dimensions are concerned, is that that's x. Okay. But notice, first of all, if this is x, then this dashed line, being the other base of that rectangle, the opposite base, would also equal x. And think about that for a second. That semicircular top would have a diameter of x, if that's the case. Now, what's the relationship between the perimeter or the circumference of a semicircle, which, notice, we're not going to count this x amongst that perimeter because it's on the inside of that shape. We only want the outside. If I think about the circumference formula for a circle, it's equal to pi times the diameter of that circle, which in this case, the diameter is x. But because I'm only dealing with a semicircle, I want half of the full circumference of a full circle. So that tells me that this, the perimeter contributed by that semicircle, is equal to 1/2 pi x. Okay? So how then can we determine the length of each of these remaining sides here? Because if I wanted to compute the circumference or the entire perimeter of this Norman window, I could really think of breaking it up into 4 parts. There's the base, there's the semicircle, and then there's these 2 sides here. And because they're opposite sides of a rectangle, they're going to be equal to each other. So let's think about that for a second. If I were to call this S, I'm going to think of that as S. How do I determine what that is? Well, we're told that the entire perimeter is equal to 200. I forgot what the units are. 200 inches. Okay, not that important for the computations. 200 inches. I could find the length of this side if I subtract from 200 the other sides. So for example, I could subtract that x, minus x. And I could also subtract away the semicircle. That's minus 1/2 pi x. And what I'm left with is actually these 2 sides, because I haven't subtracted that side. But if the remaining length here is these 2 equal sides, the fact that they're equal means I could divide this whole thing by 2 to get the length of just one of those sides. Simplifying that, that would be 100 minus x over 2 minus pi x over 4. That's how this would simplify. Okay, so I'm going to write that as 100 minus x over 2 minus pi x over 4. What else were we asked to do? We were asked to find the area of this Norman window. Well, the area is the combined area of this rectangle and that semicircle. So let's think of that now. A of x, my area, is equal to the area of the rectangle, which is length times width, or in this case, x, that's the base, times this expression, which is also given in terms of x, that's the height, 100 minus x over 2 minus pi x over 4. But I also need to add to that the area of this semicircle. And how do I find that area? Well, the area of a full circle is pi r squared, which means the area of a semicircle would be half of that. 1/2 pi r squared. But r is the radius. What is the radius of this semicircle? If the diameter is x, then the radius is half of that, x over 2. Now let's do some simplifying. So this is equal to, if I distribute my x in, 100x minus x squared over 2 minus pi x squared over 4 plus, think about this for a second, if I squared this, I'm going to get x squared over 4. If I multiply that by 1/2, it becomes x squared over 8. Then multiply by pi, I get pi x squared over 8. Okay? I can combine all three of these terms since they all have x squareds in them. In order to do that, I would have to get common denominators in these fractions, which is not difficult to do. And again, like I said kind of at the beginning of the first part of these videos, I'm not going to work through a whole bunch of algebra just for the sake of time. You can verify, however, that this becomes 100x squared minus pi plus 4 over 8 x squared, okay? It'll be a good exercise for you to show that that would be how this simplifies. All right, one more problem that I would like to do from this handout before moving along and finishing this up. Number 5, I really like problem number 5. It says that a rain gutter is to be constructed from a metal sheet of width 3 centimeters by bending 1/3 of the sheet up on each side through an angle of theta. And this picture is showing that. If the gutter is to have a length of 4 meters, we want to find a function v of theta representing the volume of that gutter in cubic centimeters. And we want to give it in terms of this angle theta. Okay? So this is like a cross section of that gutter. So E5 is where we are. If you wanted a better picture of the entire gutter, here is that cross section, but then, you know, gutter is, it's long, right? So it's going to look something like this. It's going to go down. This isn't a great picture, but you know that it gives you the general idea. So finding the volume of this gutter is a useful thing in practice because we're looking at the capacity of it. You know, how much water could it hold? And we know the length of this thing. It's 4 meters in length, which is the same thing as 400 centimeters. The reason I'm converting that to centimeters is because at the end of the day, we want a volume function that gives us cubic centimeters as our units. So that part's not so bad, but how do we deal with this cross-section where this theta is involved? So first of all, if I go like this and recreate that picture, so that's theta, this is 10 centimeters, 10 centimeters, 10 centimeters. Notice if I were to put a top on this thing, which wouldn't affect the volume, I've created a trapezoid. And putting that here, this shape is what we would call a trapezoidal prism. To find the volume of any type of prism, we take the area of the base and we multiply it by the length of that prism. So if I can find the area of this trapezoid and multiply it by 400 centimeters, that's how I'm going to get my volume. So our goal really is to find the area of that trapezoid. Now, how do you find the area of a trapezoid? From geometry, that area formula is 1/2 times B1 plus B2 times H, where B1 and B2 are the two bases. So 10 centimeters, that's one of our bases. And then this thing up here is our second base. The height is this quantity right here, okay? So what I'm going to do is see about determining what H and this second base, I'm going to call that one B2. So this, we'll call this B1, and this, sorry, it goes all the way out like this. I'm going to call that B2, Okay, I need to determine those quantities so I can find this area. So first of all, I notice that I've created these little right triangles here. And by the symmetry of all of this right triangle will be the same as this one. So that's going to be useful information. Now, the angle theta here would be the same as this angle right here. And the reason for that is because these two lines are parallel, and these angles would then be alternate interior angles with relative to this transversal. That's geometry, where you learn about that, okay? But that's a useful property because now we have an angle within a right triangle that we want to work with. Now let me take that right triangle and enlarge it a little bit. There's theta. There's my right angle. And notice we actually know the hypotenuse of this right triangle because this hypotenuse is part of that metal sheet that was bent up. It's 10 centimeters because we took this 10 centimeter stretch of that sheet metal and just folded it up like that. This would be 10, okay? From trigonometry, we can pretty easily find the length of this base and this height right here. This height right here is going to equal 10 sine of theta, and this will equal 10 cosine of theta. Think about why that's the case, okay? If you go back to trigonometry, you do a lot of stuff like this, so this shouldn't be difficult to come up with. So what does that mean? Well, if I look at the grand scheme of things, B2, this base, is split up into 3 sections, okay? I have this section here, which is 10 cosine of theta. I have this section here, which would equal 10, because notice with these dashed lines, I've cut a little rectangle out of here. So this 10 would correspond to this up here. And then this, by symmetry, would also equal 10 cosine of theta. So that tells me that B2 is equal to 10 cosine of theta plus 10 plus another 10 cosine of theta, which is equal to, I can factor 10 out of this and then combine the cosines, 10 times 1 plus 2 cosine of theta. Okay? Now also, we've determined that h is equal to 10 sine of theta from that right triangle. So let's go back to our area of a trapezoid, and let's use it in a volume formula, okay? So the volume of our trapezoidal prism, our gutter, as a function of theta, should equal the area of my trapezoid 1/2 times the sum of the bases, so 10, plus B2, which we said is 10 times 1 plus 2 cosine of theta, times the height, which is 10 sine of theta. Let's go like this. Now notice that's just the area of the trapezoidal base. I also need to multiply that by the length of this prism to get volume, so times 400. Okay? Notice if I wanted to, I could factor a 10 out of here, 1/2 times 10. I could also pull this 10 out and bring it out front, times 10. Let's move the 400 out front also. And that's going to leave me with this. It's going to give me 1 plus 2 cosine of theta times sine of theta. We could do a lot of simplifying here. What does this come out to? So I could write this as, this is 2 plus 2 cosine of theta. I could factor a 2 out of that and use it to cancel this 1/2. I have 10 times 10 times 400. That's 40,000. And what's left? Well, again, remember I factored a 2 out of this. So this becomes 1 plus cosine of theta times sine of theta. Okay. Yeah, that's what I have in my answer key. So this is our volume formula. And I could have written this differently if I wanted to. I could have distributed the sine in, for example. I'd have a cosine of theta times a sine of theta, which I can kind of work in my double angle formula for sine if I wanted to, but I'm satisfied with this the way that it's written. Notice its only variable here is theta. which is important because this should be a function of theta. Okay, so that's kind of a quick run through of some of these problems, and hopefully it gets you kind of warmed up for the kind of problem solving that we do in calculus. Again, this is all prerequisite material, but it resembles a lot of the work that we'll still be doing with the calculus added to it. Okay, so that's it for this handout.